The COVID-19 pandemic has been raging for almost over a year now, and it will be impossible for us to defeat the virus collectively and gain immunity without the protection of COVID-19 vaccinations. There are four main vaccines that are being developed and mass-produced all around the world right now. Number one is the Moderna vaccination. Number two is the Pfizer jab. Number three is the AstraZeneca inoculation. And number four is the Sputnik V made by the Russians. In this video, I will be explaining the way that these vaccinations work and which is the best to take. This will be something unique and admittedly hard to find anywhere else online, so I'd stick around if I were you. So there are two main goals when developing a vaccination. The number one and utmost priority is safety. That is what everyone has their eyes on, and if it's not safe, people don't trust it. And number two is efficacy. How many people will actually be protected by this inoculation? So there are two main branches when talking about efficacy. So number one is it protective against disease or is it protective against infection? And there is a distinction between these two that needs to be marked out. This is because when people contract the SARS-CoV-2 virus, the virus that causes the COVID-19 disease, you get a range of symptoms. Some people have very mild symptoms, so anosmia, which is loss of taste, cough, a headache, etc., etc. Some people go on to ventilators, ECMO, in the hospital, and some people go asymptomatic. So if it prevented disease, people could still get the infection, but not have these symptoms. If it's preventing infection, on the other hand, it would prevent asymptomatic transmission altogether. Okay, so now that we've established the goals, we can talk about the different stages that a vaccination needs to get to before it gets into people's arms. So number one is the preclinical phase, which is essentially animal testing. And that is done right at the start to make sure it is safe to go into phase one. Phase one is testing of a small group of people at the start who are doing that voluntarily. And this will usually be of different age ranges, but more detailed reports and data come from phases 2 and 3, which are both beta stages, so stages where there is human testing involved, but just of increasing population sizes and henceforth of increasing difference in demographics. So the vaccine has undergone all this testing, right? And it's ready to be injected into everybody's arm. So once it's in, the recipient's arm, what actually happens? How do these different vaccines work? And how are the systems similar and different? And what are the pros and cons of those similar and different systems? Well, we're going to find out right now. So the vaccine has gained EUA, emergency use authorization, and it is now in somebody's arm. Where does it go from here? Well, there are two main divides in terms of how the vaccinations work, with Moderna and Pfizer being on the same side, and AstraZeneca being on its own, as it is a different system. So let's discover these and uncover what the differences and similarities are together. So we take this orange thing, you see this orange thing over here, right? That is called a lipid nanoparticle. And all that is it's just literally a phospholipid bilayer, right? And so that is acting as like a vehicle or a transport mechanism for the mRNA into the cell. So obviously the mRNA has to be derived from SARS-CoV-2 somehow. And so we know that the thing that is involved the most with pathogenicity is the S protein. So we need to work backwards from there to find the mRNA and stick it inside the lipid nanoparticle. So we have this lipid nanoparticle invading the host cell, and it doesn't get involved at all with the nucleus. It goes straight for the ribosomes. And then, obviously, this is then going to get turned into a protein. And what is it called when we turn mRNA code into protein? Well, it's called translation. So this translation is then going to be expressed onto the cell membrane on two types of protein that our cells will express. So the first one is the MHC2 protein, and this is only found on antigen-preventing cells. And the second type is the MHC1 protein, and this protein can be found on any nucleated cell in the body. So the only real cells that have the MHC2 complexes are B cells, macrophages, and dendritic cells. And what these complexes actually do is attract immune system cells. So T helper cells, as we see here, TH, are attracted by these viral complexes. So when this interaction happens with the membrane protein and the T helper becomes activated. And so there is also another protein that interacts with the MHC2 complex, and that is the CD4 protein. And so when this happens, the T helper starts to produce a whole ton of cytokines. And what type of cytokines? Interleukin 2, interleukin 4, interleukin 5. And so what all these interleukins do is they tell a very special cell in your body to proliferate. That is the B cell. And so when the B cell proliferates, we also want it to differentiate. And when B cells differentiate, they differentiate into these very, very special cells called plasma cells. And so when all these plasma cells are stimulated and activated because of all these cytokines that are being released, they make antibodies. And guess what? These antibodies are perfect for fighting the SARS-CoV-2 COVID-19 virus.
Ladies and gentlemen, we got him.
So the second type we're looking at is the AstraZeneca method of attacking SARS-CoV-2. The way this vaccination works is actually really interesting. That brown structure there is a chimpanzee adenovirus. Don't worry, we won't have a reaction to it because humans don't have much interaction with chimps. But it's the same sort of thing as in the last two. You have that virus, the SARS-CoV-2, and you try and get the S peptide, work backwards to mRNA, to DNA, and then eventually, inside of that chimpanzee adenovirus, we have the DNA molecule. So then after you get your injection into the deltoid, the structure makes its way to the host cell, into the cytoplasm, and goes into the nucleus. And we're told by AstraZeneca that that DNA does not interfere with your DNA. Instead, it uses the host's enzymes to turn it into mRNA. Then after going through the ribosomes and expressing themselves onto the cell membrane, the rest is history. It's the same with the T helper cells, the B cells, the plasma, the little antibody soldiers, and then eventually all the way up into combating any SARS-CoV-2 that enters your body. So once again,
Ladies and gentlemen, we got him.
lots of the data on the Sputnik V vaccine has been skewed, and I do not want to add to what has been so-called the media variant, which is the spreading of misinformation just for, dramatizing purposes to get people's attention. I will just leave it as more likely working in one of the two ways, but ultimately it's going to end up producing antibodies. Now I'm going to create a table to try and rate and compare all the vaccines against each other to try and determine which is the best to take. The categories I'll be comparing are efficacy, the trustworthiness, temperature and degree C, and the cost of a dose. The efficacy of Moderna was 92% on average, 95% for Pfizer. For AstraZeneca, it was 70%, and anywhere in the range of 85 to 95 for Sputnik V. My list of trustworthiness can be, argued with and debated, but I put Pfizer as number one, especially with the number of doses that are being issued. I put at number two Moderna, just because of the efficacy rates. At number three, I put AstraZeneca, and at number four, just because of the lack of phase 3 testing, I have put the Sputnik V. So which vaccine is best? Well, obviously, at the top of my trustworthiness list was Pfizer. And Pfizer were one of the first to come out with a vaccination and have proved to be one of the more trustworthy and have administered more doses up to this point. So, it is honestly not any one person's choice. It all depends up to your demographic, who you are, where you live. But we need the protection of all the COVID-19 vaccines if we are to gain immunity and be resistant to this virus once and for all. There's been talk on BBC already about the mixing of vaccinations, which I think will be crucial as we move on and variants start to mutate. One thing that does worry me, though, is this right here. Another new coronavirus variant found in the UK. Now, these new variants are not unexpected, don't get me wrong, but it's always worrying news, because all it takes is one of hundreds of these virus mutations for things to go very far south. SARS-CoV-2 or COVID-19 has 30,000 different characters in its code, a blueprint for the virus, an mRNA virus as we established before. It's unlikely for more than a few of them to ever change in one single mutation, and usually that would die inside of its host if that got very serious. And even if it didn't die inside of its host, things could always mutate for the better. However, a few months ago, 17 of those characters changed inside one person in Kent, England. That led to an entirely new variant then sparking up. This happened inside of someone whose body was immunosuppressed, meaning that he couldn't fully get rid of the virus. And so he went back to usual being social and spread this new mutation of the virus to people who he came into contact with. The reason that I said this is worrying now that we are distributing a vaccination is because if this happened again, but instead of becoming just more deadly and just more transmissible, it became vaccination resistant, so found out how to get around the vaccinations that we have already created, then things get bad. Because then the vaccines that we've already made, and it's taken us so long to produce, would be almost useless in the face of this new variant. Why am I showing Tom and Jerry on the screen? Well, I'm glad you asked. The best way I can describe the fight between humans developing vaccinations and the vaccination mutating is an endless game of cat and mouse. And if you've ever watched Tom and Jerry before, then you'll know what I mean when I say that we are Tom in this situation. And do you know what distinguishes us from that sneaky, pesky mouse? It's the fact that we are, and we will most probably always be, one step behind. Why do I say most probably and not just leave it at that? Well, because in that slither of hope, in that ray of sunshine, there is a chance that we all manage to gain immunity and COVID-19 is eradicated. But I share the view of many scientists in just saying that I can't see that happening. Not anytime soon, anyway. You, like many others right now, may be wondering what you can do to try and prevent this from being the case, to prevent the virus from gaining vaccination immunity. And the answer is what we were doing before to prevent the virus from spreading at all. Wearing a mask over your nose and mouth, and social distancing, as well as working from home where possible. These are all the best measures one can take to prevent us from being indoors any longer than we have to. Hello everyone, thank you for watching this video. Leave what you think in the comment section down below. Also, leave a like to help this video go far on YouTube. And also, if you think this was particularly useful for yourself and you think someone else would also find this helpful, do feel free to share this to whoever you like. Also, if you're new here and you haven't yet subscribed, please do subscribe to the channel. That would mean so much to us over here. But for now, it's a bye from me, and see you all in the next one.